It's okay.
Absorption or Hilbert C.
So thank you very much. And I also wanted to thank the organizers for inviting me to give a talk here. It's certainly nice to have such an inspiring audience. So, what I wanted to talk about today is a famous theorem which is due to Kasparov, and is known as the Kasparov absorption or stabilization theorem. It states that whenever I have a countably generated Hilbert C star module, then it's a direct summand in a kind of free Hilbert C star module, so a standard module. More precisely, what I wanted to discuss is what happens to this theorem when one tries to encode some extra differentiable structure into the statement, which is given in terms of a densely defined derivation on the base C star algebra. Then I should mention that this Kasparov absorption theorem in its classical form is very important for the construction of the bounded version of the interior Kasparov product. So I also hope and expect that this differentiable version will be important for the unbounded version of the Kasparov product. So here's the plan of my talk. So first I will remind you just of the statement of the Kasparov absorption theorem. Then I will tell you which kind of differentiable structure I will put on the C star algebra and on the module. So, then with these preliminaries, I will be able to tell you the exact statement of the differentiable absorption theorem. And then the rest of the talk will be devoted to two applications of this result. So the first application is that you can, on almost any Hilbert C star module, you can construct densely defined Grassmann connections once you have this absorption theorem. So you have Grassmann connections. And then the last application, at least for now, is that you can also use the differentiable absorption theorem to construct lifts of unbounded operators. So here the problem is that you have some auxiliary unbounded operator acting on the Hilbert C star module. And then you want to use this connection here to kind of lift it to an unbounded operator which is defined on an interior tensor product. Then you want to study the properties of these lifts afterwards. So that's the plan. Oh, nice. Okay. So the first one. So there's first some general assumptions. So we have X will just be, throughout this talk, a countably generated Hilbert C star module over some base C star algebra A. So what this means is that I have a sequence X such that the A span of the sequence is dense in X. So this is over A, and then you assume that the span is just dense in X. And then there's a little bit of notation. So HA will always be standard module over A. So it consists of sequences. Of elements in A such that they are square summable. So it has to converge in norm. Okay. Oh, what do I do with this? Yeah. I hope you can remember it. All right. I can also write on this one.
Yeah, but usually it starts on the back.
Okay, I didn't. So.
Now it's too late for that.
Yeah, we will just go like that. I hope you know what Hilbert C star modules are anyway. So this is theorem due to Kasparov. And it states that there exists a bounded adjointable isometry W, which is defined on X, and it takes values in the standard module. So it's very easy to state, and it has a corollary, which is that.
What is ADJ dot?
Huh?
Adjointable.
Adjointable, yes. So the adjoint exists. Okay, so it has a corollary, which says that X is unitarily isomorphic to a direct summand in the standard module. So where P is nothing but W star. So it's a projection when W is an isometry. All right. Now what frequently happens is that the C-star algebra you are interested in carries some extra differentiable structure, and then following this scheme of non-commutative geometry, this is encoded in a density-defined derivation on the C-star algebra. Or it's encoded in an auxiliary unbounded operator. So usually you take this unbounded operator to act on a Hilbert space, but since we're interested in Hilbert C star modules, or we're interested in KK theory, we need to look at unbounded operators acting on Hilbert C star modules. So here's some extra setting. So now we take any Hilbert C star module. And then it's linked to the C star algebra A via a representation. So there's some star homomorphism from A, which takes values in the bounded adjointable operators on Y. And I will take this to be injective. And then finally we have this unbounded operator. Which acts on the Hilbert C star module Y. So it has some domain which is dense in Y. Then it is selfadjoint. And regular. Okay, so this is really terrible. Can I maybe do like this? Okay. Okay. So we'll just remind you what it means to be self-adjoint and regular. So D is self-adjoint and regular.
Press twice. Do the same. Do it twice. Twice. Do it now. Now.
Okay, so it's self-adjoint and regular if and only if it's self-adjoint. So it's equal to its own adjoint. And then you also need to require the D plus minus I. They are both surjective when defined in the domain of D. So if Y happened to be a Hilbert space, then self-adjoint and regular would just mean self-adjoint, because there you always know that the spectrum is included in the real line. But for Hilbert C star modules, there are examples where these two operators here are not surjective, even though the unbounded operator is self-adjoint. So you need this extra assumption if you want to do functional calculus, for example. So it's really necessary to use it. Okay. Then what you also frequently assume in non-commutative geometry is you have some dense star subalgebra. Which you think of as being the differentiable elements in A. And then the derivative is given by taking commutators with D. And then you assume that whenever you apply rho to an element in A, then it preserves the domain of D. And the commutator of D and rho of A extends to a bounded operator. Which I will just call delta of A. Then it's automatic that delta of A lies in the bounded adjointable operators on Y. And you can see that the adjoint is nothing but minus delta of A adjoint. Then you can remark also that this delta here defines a closable derivation on A. Okay. So let me pause for a second here. So now we have this absorption theorem, which tells you that any Hilbert C star module is a direct summand in the standard module. And then, on the other hand, I have this derivation on the dense star subalgebra script A. So I want to ask, what is the link between these two things? So more precisely, since my... let me see if I can find it. So recall I have this orthogonal projection, which comes from the absorption theorem. So it acts in a standard module of sequences. So I can think of P as being given by some infinite matrix. Then I can try to apply my derivation delta to this infinite matrix just by applying it entry-wise. Okay? So we want to consider this new matrix here of bounded adjointable operators on Y. Okay? And then, okay, you can ask several questions now. I mean, first of all, is this at all well defined? I mean, can I always assure that these entries Pij, which a priori lies in the C-star algebra A, actually lies in script A? Okay, so I don't know. So first is, does it exist?
So what is Pij? It's just with respect to a basis?
So it acts in a standard module, so there's a canonical basis.
If the basis is completely unrelated to the domain, of course,
But okay,
you can expect it.
no, I mean, this is the whole point. so usually this will not exist, right? I mean, yeah. Okay, so as you are anticipating a little bit, but okay, so now if these entries actually lie in script A, does this give me some bounded operator? So second question is, okay, so as you maybe might expect here, at least the answer to number 2 is really negative. I mean, in general, it's not going to be bounded. And there's a simple example where it doesn't hold. And it comes from the Hopf vibration. I don't know how much time I've got. Okay, I better go on. But in this case, you get that your Hilbert C star module splits as a direct sum of finitely generated projective modules, where you can assume that each of the projections is actually a smooth matrix-valued function on S2. But when you look at the derivatives of these functions, you see that it tends to infinity when n tends to plus minus infinity. So in this example, there are very natural projections where it does not hold. Okay? So I'm quite stubborn, and I really want to say something about this derivative, and in as general a situation as possible. And well, in order to tell you what can be said about it, I need to introduce a little bit of extra terminology. So there's some definition, which is just differentiable compact operators. A very, very simple concept. So here you look at finite matrices with entries in script A. Then you can just apply your derivation by applying it entry-wise. So you can define a norm. So it's just the C star norm of x plus the norm of the derivative. Well, this is a bounded adjointable operator on a suitable Hilbert C star module. Now just to note them. like the compact operators. Yeah? Yeah. Is the completion. Okay, sorry. So it's a completion of this algebra in this norm. So it's a dense Banach-Stasov algebra of the compact operators on the standard module. But the difference is that to each such element here, I can actually apply my derivation, which I cannot do to any compact operator on the standard module. All right. Okay, so until now there's no link between the Hilbert C star module and then the star algebra script A. So I need to impose some extra condition on my Hilbert C star module. So what I will assume is something very mild. So we'll just assume that, again, I have this sequence which generates x. But then on top of that, I will just assume that whenever I take an inner product of each such two elements in the sequence, then it lies in script A. So these are the only assumptions I will work with. Okay? So this is very mild. Just this. This is enough, huh? Okay. So now I can state the main theorem. Maybe, yeah. Okay, so under these conditions, what you can do is you can find, again, I can find this bounded adjointable isometry W. So that is just the same as the Kasparov absorption theorem. But then on top of that, I can also find an extra bounded positive operator K, which acts on the standard module, such that the following holds. Okay. So number one is that K commutes with the projection. So P was just WW star. Okay. Number two is that if I conjugate K with W, then I get some positive bounded operator on X, and this one has dense image. Okay, number two. Number three is that when I multiply P and K, then this is a compact operator on the standard module. All right? And then number four, which is the real deal, is that when I multiply P with K squared, then this is differentiable and compact. So I can apply my derivation to p times k squared. All right? So the role of this extra positive operator k is that it regularizes the growth of the derivative of the projection. Okay? And the tension in the theorem is that because if I just want 3 and 1 and 4, I can choose k equals 0, right? So the whole tension is that k is at the same time quite big, because when I conjugate k with w, then it has dense image. So then it becomes less trivial to find this operator.
You can replace k by k squared, and then you can forget about condition 3 and just write that pk is differentiable compact.
This you can do, okay, but I wanted to...
This makes the theorem simpler.
It makes the theorem simpler, but you do not... I mean, what is suggested also here is that if you continue and you had more than one derivation, then you could obtain stronger results, right? If I multiply p with k third, then I would get a C2 condition instead of a C1 condition here. So that's why I was stating it this way. Yeah. All right. Which I didn't prove, but I'm quite certain that it's possible. Okay, maybe I tell you shortly how these W and K are constructed, because it's interesting to see. Because it's really, they are very concrete operators. You can write them down explicitly. So we'll just do it in the most simple situation where x is generated by a single element, but not algebraically. So you're allowed to take closures. So you have many interesting examples where this is the case. Then you have this inner product is in script A, of course. This is the only condition. And then what you do, you can already define what k is immediately. So k is just a diagonal operator, which has the inner product of psi with itself on the diagonal. So this is some positive operator on the standard module. Then you define two maps, which are the most stupid ones you can come up with. So you define phi from x to a just by taking the inner product with psi. Then this is adjointable. And the adjoint is just given by multiplying with a from the right. Okay? Well, these are very simple maps. And then there's one observation, which is that then I can form a sequence of operators on x. Just by taking phi star, and then psi inner product psi, plus 1 over n, inverse, and phi. So phi goes from x to a. This is a bounded operator on a. And then I can go back with phi star. And then you prove that it converges strictly to the identity operator on x. So this is the only observation you really have to make. Because then you can define what is W. And here you really use that X is generated by a single element. Otherwise, this is not true. Okay, then you define W. So at some element eta, I have to define some sequence. So what I do is that I look at the, so square root plus 1 over n inverse minus we have to finish the square root. And then there's phi of eta. So this gives me some sequence of elements in the standard module, and you can prove that this is an isometry. Yes. Then you have to prove all this stuff here, but it's quite standard now. Once you have this explicit form of W and K, then you can prove the rest. It's not so hard. So this proof here, I think, is also quite different. It's different from the usual proof of the Kasparov absorption theorem. Because what you do there, you always stabilize by adding the standard module. Then on this new module, you can, for example, do Gram-Schmidt orthonormalization. Then you get some orthonormal basis, so the direct sum is isomorphic to the standard module again. But when you do Gram-Schmidt, it's not very explicit because it's defined recursively. And if you want to try to start computing derivatives, I mean, you're soon going to die. I mean, it's really horrible. So you really need this idea to prove the differential absorption theorem. All right. Then I want to talk about the two applications. Okay, so as now you can construct Grassmann connections. So I will just make one definition first. So I just need to remind you what is the continuous delta form, so for me at least. So it's just the smallest. C stars of the bounded adjointable operators on Y, which contains all the elements in A and then all their derivatives. So it's a little bit crude, but then what you can prove is that now I can construct, using this absorption theorem, I can construct some dense script A submodule script x of x. So there are very general conditions now. I can always find this then script a submodule and a C-linear map nabla delta, which goes from script x and takes values in the x-valued continuous delta form. So it's the interior product of x with omega delta of a. It's only C-linear. And, well, it's a connection, so it satisfies Leibniz rule. So when eta and a is in script, eta is in script x and a is in script a, this is just nabla delta of eta times a, and then you have eta tensor delta of a. Then you can also prove that it's Hermitian. So, yeah, I should have told you a little bit more. Okay. Yeah. Let me just write it down. So when I apply delta to an inner product of two elements in script x, what I then get is that this is, okay, there's some pairing which I will tell you what is. So it's eta paired with nabla delta of zeta, and then minus zeta paired with nabla delta of eta in the adjoint. So the adjoint just takes place in here, in these continuous delta forms. It's a C-star algebra, okay? So I just tell you what this pairing is. So it takes, this is a continuous delta form. This is a vector in x. So I start with a vector in x and a continuous delta form. And then what I have to produce is a continuous delta form. So it just maps eta and zeta tensor omega into the inner product of eta and zeta. Oops. Multiply with omega. So it's the most simple thing you can do. And then it's, my Grassmann connection is also Hermitian in this sense. Now we are ready for the last application. So I said I wanted to construct these lifts of unbounded operators. So now I have, throughout this talk, I had this unbounded operator D, which acts on the auxiliary Hilbert C star module Y. Okay? Now I have succeeded in constructing this connection here, nabla delta. So I want to use these two objects to define a new unbounded operator, which is defined on the interior tensor product of x and y over A. And it's given explicitly in terms of the connection and the unbounded operator D. So that's the last part of the talk. Okay. So that's first a small observation. So we had this bounded adjointable isometry, which comes from the differentiable absorption theorem. So we can define W tensor 1 which is now on the interior tensor product of x and y over A. And it takes values in the bounded adjointable operators, the standard module over y. So these are just sequences of elements in y such that their inner products converge in norm. So they're square summable sequences in y. Okay. And this is again a bounded adjointable isometry. Okay. Now you can also define, so you have this unbounded operator D which acts on y. So I can define just a diagonal operator given by D. So it has some domain, and it takes values in hy. So what does it do? It takes a sequence of elements in y such that each entry lies in the domain of D. Then I just apply D entry-wise. So it's very easy definition. And so the domain is also really precise here. So that's important. You always have to specify what the domain is. So there are just sequences here such that each entry lies in the domain of D and such that this image here still lies in the standard module. So this is very precise. And you can prove now that since D is selfadjoint and regular, then this is also selfadjoint and regular. This is not hard. Oops. Okay. Now the most simple thing you can come up with is that you can conjugate this diagonal operator D by your symmetry. So we just define the symmetric lift, which is called 1 tensor nabla D. And it's defined on it has a precise domain, which is just all elements in the interior tensor product which are mapped by this isometry into the domain of the diagonal operator. So you can really define what the domain is. There's no doubt about it. And then it takes values in the interior tensor product. Okay, what is it? As I said, I just conjugate my diagonal operator with this isometry. Fair enough, but what is absolutely non-obvious now is that this is densely defined. If I had chosen any bounded adjointable isometry for this absorption theorem, it would not be densely defined. Okay? So I need the differentiable absorption theorem to prove that this one is densely defined. Okay, what can you prove about it? So this is just a lemma. Well, you can prove that it's symmetric. This is no surprise. Okay, what you can also prove is that when I apply it to special kind of elements, then it's given in terms of D and the connection, just as I promised. But you need this alternative description here to find out what the correct domain is. All right? So when I apply to an element x tensor y, where x is in script x and y is in the domain of D, then this is nothing but nabla delta, so the Grassmann connection applied to x, evaluated at y, plus x tensor E of y. So there it has a very explicit description, but you need the isometry in order to define the domain correctly. Okay. Oh, I'm short on time, but okay. What?
You got only 15 minutes, 12, 15 minutes.
13.
Yeah.
Ah, okay, my watch is a little bit ahead of time. That's why. I cannot see that one. So. Okay. 13 minutes, that's good. Okay. Okay, so questions are, now I have this nice unbounded operator, I can ask, is it going to be self-adjoint? Okay, is it also going to be regular? Okay, and I think the answer to both of these questions is no. Unfortunately, it's no. And I do not have a counterexample to this one, but I can give you one to the self-adjointness. So I will maybe do this. So it's an example. So now you take the Hilbert C star module X to be just continuous functions on the half line that vanish from 0 to infinity. Okay, this is a Hilbert C star module over the continuous functions on the real line that vanish at plus minus infinity. In a very obvious way. And well, here I have a nice representation and a Dirac operator. So rho is just acts on equivalence classes of square integral functions on the real line by multiplication. Pointwise multiplication. And D, so my auxiliary Hilbert C star module is now just a Hilbert space, so these square integrable functions. And D is just going to be the Dirac operator over the real line, which has domain the first Sobolev space on the real line, and it takes values in this Hilbert space of square integrable functions. And script A is nothing but smooth, compactly supported functions on the real line. And then you can try to do this stuff, right? So you have, now x is generated by a single element because there's a nowhere vanishing function, so you can just try to do the construction and see what you get. And yeah. Okay, you check it. So one tensor nabla D is a symmetric extension of the following unbounded operator, which is just a Dirac operator on the half-line. So it has domain, say, continuous, smooth, countably supported functions on the half-line, and it takes values in the square integrable functions on the half-line. So then this unbounded operator here, it has no self-adjoint extensions because the deficiency. Yeah?
Are you saying that one tensor number B has this specified domain?
No. I'm just saying that this subset here is included in the domain, and yeah.
Do you specify the domain of the other one?
I didn't do that. No, it's a little bit complicated. It depends on the function you choose. Yeah. I mean, you cannot see. Yeah. Probably it's a closure. I mean, I don't know. Yeah. I didn't do that, so. But at least it shows you it's not self-adjoint, which was my main point for now.
No, it doesn't show anything. I mean, it just says it's a symmetric extension. It doesn't show it's not self-adjoint.
It has no self-adjoint extensions. Yeah. So it does show it's not self-adjoint. Okay. Good. Okay, very good. And yeah, so those are maybe terrible news. It's not going to be self-adjoint in general.
The closure of this has no symmetric extensions because of deficiency indices, so you know what it is.
But
It's Kaad in the color of symmetric.
okay, maybe.
Closed, it must contain the closure.
But I don't know whether it's closed for the moment. I didn't say that, but yeah, you can close it and.
Still, I don't find this example too convincing because it's really a problem of deficiency indices which are already visible in Hilbert-based context and have nothing to do with the Hilbert module.
It does have something to do with my Hilbert module. I've chosen the Hilbert module such that this does not, such that this fails. Okay? For many other Hilbert C star modules, I would always get self-adjoint operators. It's because I have chosen something which comes from a non-complete manifold. No, that's why. I mean, you cannot get rid of this problem, no matter what you do. If you want to work with this Hilbert C star module, this will show up no matter how you try to define the lift and all that stuff. Okay. That's how it is. I mean, I'm pretty convinced about it. Okay, so those are terrible news. And so now we want to find out what to do about it. Okay, so I really want to have some lift which is well behaved. So now you define an extra operator which solves this problem for you. And this is where this extra bounded operator k comes into play. You can really see it now. So now you define delta, which is just given by conjugating k with w and then tensorizing with 1. So it acts on this Hilbert C star module. And it's positive and it has dense image. Because this was true for W star KW. All right. And then what you do is that you modify this symmetric lift by multiplying with delta from the left and from the right. Yeah, like this. This is good. Maybe it's k squared. Let's do it like that, just to be safe. So then you can prove that if I look at delta 1 tensor nabla d delta, and again it has a precise domain. So the domain It's just everything which is mapped by delta into the domain of the symmetric lift. Then you can prove that this is essentially self-adjoint and regular. So the closure of this unbounded operator is both self-adjoint and regular. So I think this is the right lift to work with. All right, so it was possible to construct a nice lift, but it didn't really have the expected form, because you need to modify it by this modular operator here. Unfortunately, but I don't think there's any way out of this. So that was what I wanted to say today. Thank you very much for listening.
Does the regularity proof use our particular?
Yes. Yeah. I mean, it's not clear that this is regular at all. I mean, you really have to work. Because, yeah.
When you are looking at the Kasparov construction of the product, okay, you have some formula for the form T tensor 1 plus 1 answer the order of electron. And you have also the problem to define what is 1 answer the order of electron.
Mm-hmm.
You use, in fact, the connection in order to do that.
Yeah.
And it seems to be very related to what you are doing here, because in order to get Kasparov proof of the existence of this product, the connection, well, essentially, he is looking into some approximation of the identity. Okay? So my question is, in the construction of Kasparov, this element is not very well defined. It is defined up to contact operator.
Mm-hmm.
So my question is, when we are looking now pure element,
Mhm.
what is the relation with the ones that we can construct by using Kasparov product?
So there's a very... This is, I mean, it's a nice question, of course. Because what you want to prove is that this kind of operator here, which I've constructed, this one here, that in the case of an ideal, which was what I was looking at here essentially, okay, then you want to prove that when you take the bounded transform on this one, then you get the Kasparov product. And there are lots of similarities in the construction, because how do you find this operator 1 tensor T in the bounded picture? You also have to stabilize first. This is exactly what is going on here. I mean, I choose this W, and then I can just conjugate the diagonal T with W. So it's the same structure, but it's harder because everything is unbounded. So there are many more things that can go wrong when you start doing it. So, yeah. Or it has different difficulties. I would maybe say it that way. That's more correct. So.
Okay. Can you directly relate the size of this delta to the growth in the derivative projection? I mean, they're clearly related. Is there a direct relationship between them?
Yeah, that's quite clear what happens. I mean, because everything is explicit. So your W looks like a square root of 1 over n plus something inverse. Yeah? And when you take derivatives of this, it starts growing. Yeah. And then when you plug in an extra, I mean, when you plug in delta, you can just see that. Yeah, exactly. That's exactly what is happening. Mm-hmm.
So what is delta in example?
In this here, it's the square of your nowhere vanishing function. You've picked this nowhere vanishing function. Do you think about the half line now? Yeah. In the half line, you have to choose a generator. So it depends on the choice of generator of your Hilbert C star module. So if you choose some nowhere vanishing function f on the half line, then delta is just the square of f. Yeah. I mean, you have to. Yeah. Sure. I mean, it should be smooth and all that stuff. I mean, you cannot. Yeah. You cannot do it with any function. No. This is implied because you need to have f squared is in the C star algebra you start with, or in the dense star algebra you start with. So that fixes the smoothness condition on that element.
But intuitively speaking, on the half line, if you shift to the left, you lose something, so you cannot go back. And that makes this different efficiency indices. Now, there's a trick in quantum mechanics by adding another operator, actually.
Yeah.
So that the sum does it. And maybe that's really interesting.
Yeah, it's not far away from being 1 tensor nabla d plus 1 over f squared or something like that. Yeah. It's quite. They're very related, these two operators. Yeah.